So now let's prove one of the three major theorems that were given to us, that the antiderivative with respect to x of basically 1 over a squared plus x squared, where a is not equal to 0 in this case, is going to actually equal 1 over a arctangent x over a plus c. So let's prove that. And of course, how do we prove when we take an antiderivative of something, how do we check and verify that it's right or correct? We're going to take the derivative of the right side and make sure we get what's within here. So what's within here, I'm going to rewrite this as 1 over a squared plus x squared with respect to x. So really what I want to do is I want to make sure when I take the derivative of the right side with respect to x in this case, because that's my variable, when I take the derivative of this, I want to end up with 1 over a squared plus x squared. So let's prove it. Proof of the theorem here, I'll go back to black, might be a little bolder here. But anyway, when I take the derivative with respect to x of the right side, remember a is a constant, so it's just a number. So is c. C is just some arbitrary constant, right? So the derivative of the sum is the sum of the derivatives. Of course, the derivative of a constant is 0. So I can essentially ignore that after I take the derivative. But 1 over a, if a is a constant like 5, then 1 over a is also a constant. It would be like 1/5, right? So the derivative of a constant times a function is the constant times the derivative of the function. So it's 1 over a times the derivative of the arctangent of x over a. So really what I'm going to do is 1 over a times the derivative of this. Well, what was the derivative of arctangent? So let me use the derivative with respect to x. Well, actually, let me use u because this isn't just an x here. The derivative with respect to u of arctangent of u actually equals 1 over 1 plus u squared, right? And then times the derivative of u with respect to x, so times u prime. Okay, so when it's some function of x, when u is a function of x like I have here. So the derivative of arctangent is going to be, let's take the derivative of this part, so it'd be 1 over 1 plus that thing quantity squared, so x over a quantity squared, but then times the derivative of that with respect to x. Well, x over a is like 1 over a times x, right? So like if a was 5, x divided by 5 would be like 1/5 x. The derivative of that would be 1 over a, right? So it's just the derivative of a constant times x is just the constant. So this would be times 1 over a. And then, of course, the derivative plus c we already said was 0. So we have this, which doesn't really look like what's in the red up here, but we need to try and make it look like that, right? So let's go ahead and simplify this a little bit. This is all multiplication here, so I'm going to take 1 over a times 1 over a, and I get 1 over a squared. And then times, now the blue part, or this part right here, let's rewrite that a little bit. So 1 over, really this is 1 plus x squared over a squared, right? If I go ahead and square that out. So what I'm going to do here then is I'm going to rewrite the denominator by getting a common denominator. So the 1 over a squared is still there, and then times, if I get a common denominator, it's 1 over, 1 would be a squared over a squared, right? And then plus x squared over a squared, right? And of course, how can I rewrite that? I could rewrite that as, I'm going to come over here. So that's 1 over a squared is still there, but then it's going to be when I got a common denominator, I can just add the top and keep the denominator. So it's going to be a squared plus x squared all over a squared, right? And of course, with this one, we're dividing by a fraction, right? So instead of dividing by a fraction, what we can do is invert and multiply. So just if I divide by 2/3, that'd be the same as multiplying times 3/2. So this is equivalent to 1 over a squared times the reciprocal of the denominator, which is a squared over a squared plus x squared. And what do we notice here? we noticed that the a squareds would cancel out as long as a doesn't equal 0, because a squared divided by a squared is 1 as long as a doesn't equal 0. So that's why when we originally have this, they put a restriction that a can't be 0. Because 0 divided by 0 doesn't cancel out, it's actually indeterminate, right? So we talked about that back in Calc 1. So anyway, this is equivalent to 1 over a squared plus x squared, which, believe it or not, is what we had in the red up here. So by taking the derivative of the right side, we ended up with what's in between the antiderivative and the dx here. So this is a proof that the definite integral with respect to x of a squared plus x squared, as long as a doesn't equal 0, equals 1 over a arctangent x over a plus c. And then, of course, we did mention in class, but if a would actually be 0, we could do that one as well. So let me just do that one in purple. If a were to be 0, I can go ahead and erase this now. But if a were 0, we could still take the antiderivative, but it doesn't have anything to do with the arctangent function. If a does equal 0, we have simply the antiderivative with respect to x of 0 plus x squared is x squared. So I could rewrite that as the antiderivative of x to the minus second power with respect to x. We can simply just do our power rule, and that would be add 1 to the exponent, x to the minus 1 divided by that, plus c, which of course then that x to the minus 1 drops down. The minus sign can come out front, so it's minus 1 over x plus c. So if a does equal 0, we can still do it, but once again, doesn't have anything to do with arctangent. So there's the proof of the second theorem that they gave us on there. So I'll let you work on some of the others that we didn't do. Enjoy.